we changed a little bit the program according to what was on your on the schedule, and I did here a lecture on Variscan, which illustrates the transition from Precambrian, that we're going to treat at last, to Phanerozoic. And the Variscan is a bit in between in terms of behavior, geological record, and you will see that at the end. So what is the, so some of the slides actually I didn't have time to translate them from French to English, but it doesn't matter much. So this is the compilation map done actually. It's funny, I didn't realize that. I showed you in the first day the first geological maps of France and Germany, and this one was earlier. I'm not sure why. And this one is France and Germany. And roughly we see the same things as what we see in the French and German maps. So I wonder how this guy managed to do a synthesis before the actual maps were published. So I have to dig into that, into history, understand how it happened. But nevertheless, what happens here is that we see this red belt, this massif with red colors. This corresponds to the Variscan belt, and it's partly overprinted by the Alpine belt. And this was recognized by two geologists at 1 year interval. Edward Suess, who is a guy working in Austria, and he named that belt the Variscan belt, based mostly on stratigraphic and paleontological evidences. And then the French guy, Maurice Bertrand, 1 year later, called the same belt Hercynian. And it's based mostly on the lithological units, structures, and structures. So you have two names for the same belt, and it's still present in the literature. Strictly speaking, we should talk about Variscan because it was the first one to be defined. But both, they consider that this mountain belt is from post-Cambrian age and pre-Permian that forms a large part of the basement of Europe with similar structural paleontological characteristics. So what is peculiar about the Variscan belt compared to the Alpine Himalayan belt? Well, at first glance, all these red and pink corresponds to migmatites and granites. So lots of migmatites and granites. And I'm sure here, some of you work on the Proterozoic Archean, and that's what it is, lots of migmatites and granites. So that's why I'm calling upon the transition between Archean to Phanerozoic. The more you go back in time, the more granites and migmatites you find at the outcrop. So that was the case also for the Variscan. It's more granite and migmatites than the Phanerozoic. A wide, and this brought the idea of a cynotype versus alpinotype, to distinguish the two types of belts. And what are the characteristics of the cynotype compared to the alpinotype? Is very wide belt compared to alpine, except in the Himalaya, if we consider Tibet as part of the belt. No naps, we'll question that. No tectonic naps. At first glance, it was lots of granites and was not obvious to identify naps. No ophiolites, or very little ultramafic rocks. Metamorphism dominated by high temperature and very seldom high pressure, and lots of granites and migmatites. And you notice that was proposed by Henk Zwart, a Dutch guy, in 1967, just at the onset of plate tectonics. So the question was that at that time, okay, was the Variscan belt formed the same way as the Alpine belt, in terms of plate tectonics? Was plate tectonics already active at that time? So we're going to challenge all these points. So the Variscan belt is outcropping exposed in various massifs, partly overprinted by the Alpine belt, but we can find evidences of it throughout the continents, even going across the Atlantic in North America. All this is part of the Variscan belt, and if we might also put the Ural into the play, although it's a bit younger, sorry, a bit older. Okay, and you see it follows roughly the same trend as the Alpine belt, Alpine Himalayan belt. So it means that probably the same cratons were involved, going apart from each other and then going back closer to each other, going apart and going back. So it seems that we have a repetition of the scenario, Alpine belt, I mean Variscan belt, and then Alpine belt. Opening, closing, opening, closing. And the scenario in terms of plate tectonics was proposed in the late 20th century, early 21st century, with basically the closure of a Paleo-Tethys ocean that was associated with accretion, tectonic accretion of continental ribbons and intervening oceanic domains, pretty much the same way as for the Alpine Himalayan belt. And then at the end, big continental masses, Laurasia, which is composed of Laurentia, North America, and Baltica, Siberia, all the cratons forming the European part, East Europe, and Pangaea, basically Africa, South America, India, Australia, and Antarctica. And this was reconstructed thanks to paleopoles record in continental rocks. I'm not sure I want to go into details of that. No, I'm going to skip that. But there are records, and you can see basically that the poles for Laurentia and Baltica Europe, at some point, they merge, and before that, they were far apart, so it allows to reconstruct the motion of these continents. So another illustration of this model of starting in the Ordovician, formation of continental ribbons along the coast of Gondwana, and that's after the Pan-African orogeny. So after the Pan-African orogeny, there was some kind of collapse, I would say, and opening of new oceanic basins that will delimit continental ribbons that will then move with the cratons towards the north and be accreted. So it's this sense. So they move like this, and then they are tectonically accreted to Laurentia. And then at the end, the two continents get in touch. So there are several sutures that are identified. The first one is actually the first orogenic event is the Caledonides between Laurentia and Baltica, and that results in the formation of Laurasia. And then this is identified as one of the continental ribbon, Avalonia, and it's the first step of the Essenian or Variscan orogeny. And then you've got sutures, one running here, another one running here, and then the Alpine orogeny that is superimposed on it. And you see that there is a strong limit here, which is the boundary of Baltica, Ukraine. So the strong craton that is not overprinted neither by the Variscan, nor by the Alpine. So that's a strong block that doesn't get reworked. But the material in between, this and this, is being involved in divergence, convergence, and tectonic accretion. So how does it look like at depth? So this is a seismic reflection profile going all the way to the Moho, and the Moho is here at about 35 kilometers, and that's in northern France, beneath the Paris Basin. The Paris Basin is filled with Mesozoic and Cenozoic sediments, but underneath we find the basement. So that's the basement. Here on top of that Precambrian basement, and that's something we're going to also question, what is the meaning of that Precambrian basement. But here we see a Paleozoic cover, which is detached from its basement with following thrusts. And then you've got the Mesozoic sedimentary cover, carbonate. And what is interesting here is that, okay, what is your feeling about the structures that you can follow from surface geology and you can follow down at depth compared to the moho? What is peculiar in the lower crust? You see there's lots of reflection here. And that tells us that there are lithologic contrasts that are horizontal, with rocks that change, from fast to slow, to fast to slow propagation of seismic waves. So it shows that there is some kind of horizontal layering here. What do you think about these structures? How do they relate to this? Who is cross-cutting which? Do you think that these structures that are oblique are cross-cutting the horizontal one, or the other way around, the horizontal ones are cross-cutting the steep one? Is it not clear enough? I think you see it even better than when I'm closer. What do you think? Take responsibilities. Who's cross-cutting which? So. Horizontal is cross-cutting, right? So in terms of relative chronology, you would infer that this occurs after that. And this, you see here, it's kind of either routing or at cross-cut. So the Variscan front, which is here, is rooted in horizontal layers, or cross-cut by horizontal layers. So we'll come back to that later. So the main methodology at first was to rely on unconformities. That's a wonderful unconformity between the Trias and the Carboniferous. The Trias is the new how do you say that? Marine increase, no? The level of marine level was increasing and covered all the basement after the Carboniferous and even after the Permian. And you see that in Portugal with Carboniferous rocks being folded, sedimentary rocks being folded and covered by Trias. So this was done in several places, and several unconformities of different ages were identified in the Variscan belt. And this allowed to sort of reconstruct tectonic phases of different age as reconstructed thanks to these unconformities. And this didn't really rely on granite or migmatites, and didn't even consider much the difference between gneisses, paragneisses, schists, and orthogneisses. Just considered sedimentary stratigraphy. And that's pretty much the story everywhere in the world. We started with stratigraphic reasoning, deformation of sediments, and everything that was underneath was basement. So now we are at a time where it's needed to go further and to work on what is this basement. What does it mean? What is its geological record? So from these first investigations, so the different crustal blocks were identified, Avalonia, and another one, Armorica, which is exposed in Brittany, and that might be also identified in the Bohemian Massif in Czechia. And that's also, there is probably a continuation of it in Iberia. And all the red lines are either deformation fronts and sometimes, or most of the time, related to sutures. Okay, and so in order to account for this alternation of continental and oceanic zones, several models have been proposed. First, here, monocyclic doubly divergent subduction collision with Armorica in between. Laurussia would be on my right, and Gondwana is there on the left. So you see closure of oceans with subductions. And here it's a slightly different model, so it's the same time frame during the Silurian here, which marks the onset of subduction. Here they propose that the margin of Gondwana was hyperextended during the Ordovician, and these are the Ordovician blocks. And here to the north, also several blocks. And then a first stage of oceanic subduction was followed by continental subduction. And in this model, they put more emphasis on that subduction. And then a switch from that polarity to that polarity, whereas in this model, both are concomitant. These are details, but what we can gain from that is really a view that insists on the fact that there are basement and cover, and we work on that in order to reconstruct the tectonic phases. Little bit of magmatism, but not much. Except at the end, in this model, so it's a compilation of the work of several authors. I made sort of a synthesis of what they proposed. It's the only model where they propose a bit of melting of the orogenic root that will feed granites. Okay, so that's the general picture. So now we're going to move to the French Massif Central, where I told you I started my investigation as a geologist when I was about the age of the bachelor's here. So that's how it looks like. And in these models, what is taken into account is all the brown, green, yellow rocks, which makes about half of the outcrop. Half of the rest of the outcrop, so the brown and stuff, it's all the gneisses and mica schists, from low grade to high grade, with their protolith, Pan-African, Cambrian, Ordovician. Some might be Ediacarian, that's late Proterozoic. And and the rest, the other half is granitoids and migmatites, with protoliths that are difficult to identify because the rocks are so transformed, it's difficult to identify which origin they had, orthogneiss or paragneiss, and even more, their age. What you can date in these rocks is the age of crystallization of the granite, crystallization of the mimetite. And you might preserve, in some cases, you might preserve some accessory minerals that are inherited from the protolith of these rocks, sedimentary, might be detrital zircons, or it might be also magmatic zircons inherited from the protolith. And then there is also a sedimentary and volcanic deposits during the Variscan orogeny, from late Devonian here to all the way to post-Permian, that's the gray. If we compare the colors, that's the gray here. So migmatites and granites, they account for 50% of surface exposure. And if you look at the age of the migmatites and the granites, their crystallization age, it goes from 390 to 285, more than 100 million years. So that's a long thermal event. So let's first try to identify tectonic units. And this was done in the 70s and 80s, almost 50 years ago, where people identified this particular unit, which is made of amphibolites and leucogneiss, what was called at the time leptinite. So an alternation of that was considered to represent an alternation of basalt and rhyolite. So if I'm placed in a rift environment, the basalt having a tholeiitic signature. And these, the potolith of these are now metamorphic rocks. Potolith of these has been identified as Ordovician. So the time of extension of the Pan-African belt and opening of small basins on the edges of the old cratons. The tholeiites have they are pristine basalts, pristine metamorphosed basalts that were extracted from the mantle. They contain also ultramafic budines. So this was interpreted as an ophiolite. Okay, that's the first point of Svart. You said no ophiolite. Huh? Maybe we found them. It was not easy to identify as such because it's so deformed and metamorphosed, but these are good candidates for being former ocean. So how are they distributed? It's all the green here on this map. So it's kind of dispersed. So it's not easy to trace a line from these. No? Not a nice suture like in the Indus Songpo suture. So this author called it a sort of a cryptic suture, which was dismembered during orogenic evolution. And that, so leptinite and fibolite complex, that's the name that was given to that particular complex. And we'll see that later on that it has recorded eclogite-facious metamorphism. This should remind you something about what we talked about yesterday. Mafic budines with eclogite-facious. Where was it described? In the Himalayas? Somorawi. So this lac is here identified in that section by these black budines. And it was used to distinguish between what is below and what is above. What is above has been called the upper gneiss unit because it's made of gneiss. And what is below has been called the lower gneiss unit. It's also made of gneiss. So yeah, and the first scheme proposed here by Burg and Matt. And by the way, Burg was my advisor for the master. He said, okay, we see that succession 1, 2, at least 3 times. So we had 3 naps with upper gneiss unit, leptinite and fibolite complex, lower gneiss unit, and then repeated with clipper and complex structures. So if we have 3 naps and 3 sutures, that means 3 small oceans. In between. That's the way separating continental ribbons. And that was then re-evaluated by Mattauer, who was the big tectonic guy at the time in France. And he said, okay, I've been to the Himalayas. In the Himalayas, there is one big thrust, and let's apply that to the French Massif Central and the Variscan. So he probably never went there. He was in the Himalayas, but not much in the Variscan. But he was, a big talker. He said, okay, simplify. With 3 naps, I do only 1. With upper gneiss unit, Laurussia. The ocean is the leptinite and fibolite complex, and the lower gneiss unit is Gondwana. Just take 30 seconds here, see how much of a stretch it is, to go from this distribution of rocks, ultra-mafic rocks combined with mafic rocks. Say, okay, recognize that they have a tholeiitic, basaltic nature. Say, maybe they are remnants of oceans. They are sort of dismembered into gneisses, and everything which is to the north and on top is North America or Laurussia, and everything which is to south and below is Gondwana. There's lots of interpretation there, right? Lots of concepts. And this was the last proposition of that type of models with here also a single nap. And the same author, Matt, proposed to align with Mattawa and proposed only a single map with a bit of refinement of the coastal scale structure with thrust affecting the basement and the cover. That would explain the formation of these antiforms that are also identified as domes in the field. And representation of the granite, I mentioned that. Granite, we don't know from where they're coming. No, there's sort of there's no source of this granite. They are rooted in a basement, which is not identified as migmatites. So what is the source of this granite? Do they relate to the migmatites? Where are the migmatites? More recently, some authors propose, okay, we're going to acknowledge that at depth, below, say, 10 kilometers, we have no idea about the structure. So they called it unknown Proterozoic basement. That's safer, right? There's no interpretation. So then we'll question, okay, how does this basement relate to all the migmatites that are outcropping in the French Massif Central? So let's tell the story, the metamorphic history that is recorded in different units that have been identified according to the position relative to the leptinite and fibrillite complex. So at first, you have all these purple and orange rocks, which are depicting pressure temperature field in the eclogite fissures. So you have eclogites throughout. That corresponds more or less with the suture rocks. The suture rocks, most of them have recorded eclogite fissures, which means burial. And burial, in terms of geodynamics, what is the most simple way to account for burial in terms of plate tectonics? Subduction. And then, superimposed on that eclogite fissures metamorphism, there's granulite, high pressure granulite, and then low pressure granulite. That is recorded and identified by not the ACK, but the plain pink and plain orange. So that means exhumation. And then all the green here is green schist fissures, amphibolite fissures, the strong green, and the light green schist fissures. So then there's been, and that's in timing, I didn't mention that, but that's dated, at first it was dated 430 to 400, but refinement of these ages tends to be younger, and it's more closely to 380, but that's not the problem. 380, and then granulite fissures 370, amphibolite to green schist fissures 360. And then continues from all the way to 345 and covers pretty much all these rocks at 345 where under green schist fissures, some towards amphibolite fissures. At this time, the main stretching direction is parallel to the belt. And it's a time of emplacement of leucogranites in the northern part of the French Massif Central, and along this structure, which goes across the belt, it's a transfer fault, which is called the sillon houillé, houille meaning coal. And it's the place where all the coal basins have been formed along a large track slip fault. And that's what has been exploited in France for 2 centuries and is now finished. And at the end, 320 to 290, the large migmatite dome here in the Velay, that we're going to come back, emplacement of other granites around, and here another dome in the southern part of the Massif Central, which I'm not going to talk about. Okay, and that's history. This is what, I'm coming back, sorry. Yeah, this is what fed this model, this one, with first oceanic subduction, continental subduction was following, and then coming back, yeah, and then break off of the lithosphere. Made a mistake here. 360, 60. Ah, yeah, that's right. Okay, so it's a switch of subduction from northward subduction, and then the next step, it's switched to a southward subduction. And in this side, it's not clear how, but there's costal thickening that continues, and that leads to the formation of the migmatites. But migmatites and granites are not fully taken into account in that type of models. So that's what I'm going to correct and reappraise now. As I said, yeah, we cannot miss 50% of the outcrops. We need to take that into account. So at first, we went to, so that's in this part here, you see that there is these green units, that's the suture. And we went to investigate, so we're going to now restrict ourselves to this area. And the top structural level are these units, the suture associated with the upper gneiss. And then we move to the lower gneiss and eventually to the migmatites that are the pink zone here. So the upper gneiss is associated with these green units, and it's put in contact with the lower gneiss and the migmatites along this myonite. This myonite is here in cross section, so that's the migmatites and the lower gneiss unit. And on top, you see you have the suture rocks, mafic and ultramafics. And here we can see the arrows, they point towards decrease in metamorphic gradient. So metamorphic gradient is decreasing this way, but also this way. In other words, here there is an inverted metamorphic gradient. And then, as we go down, we go from here, amphibolite fascias, and then all the points, the dots here corresponds to migmatites. So there's another metamorphic gradient pointing upward this way. So it's a quite complex structure, with decreasing this way, and decreasing this way. And here you have a meeting point between the upper gneiss unit and the lower gneiss unit. So how does it look like? Well, here are the amphibolite budins with eclogitic relics. And you see around is a lot of granite and very heterogeneous. We can call that a diatexite. I'm not sure how much you could see from yesterday's presentation, of Malika's presentation. Does it look like the association that was shown yesterday? You say, I see yes, I see so-so. No? Yeah, I think the main difference is that from what he showed yesterday, and this is maybe subtle, there was a strong solid state fabric surrounding the budins. Whereas here, it's not easy to tell from the distance, but you have a magmatic texture that is preserved. And I think we can make the assumption that it was the same for the eclogite in the Somorari, that they were embedded into migmatites, and then there was a strong solid state deformation overprinting the magmatic textures. And magmatic textures are preferentially preserved around the budins, in the budins' necks, or as inside the budins where you see veins coming into it. But here it's also pervasive. Most of the fabric is magmatic. In other words, these mafic rocks that went at depth about 100 kilometers, coesite was also found, and same as in the Somorari, are embedded in granitic rocks, diatexites, heterogeneous granite. What does that represent in terms of paleogeography, we think? Granitic rocks. Oceanic crust or continental crust? Continental. So the ocean met the continent. at some point. So we have to keep that in mind. And where did that happen? Did that happen during, and when? Did that happen during eclogite phases, or before or after? Yeah. Yeah, but that's the concept. But now what do we see on the outcrop? We see that the Boudins are wrapped into migmatites that are granulite facies. So I think from the field relationship, we can say that granulite facies occurred after eclogite facies, but the time at which these mafic rocks were put in contact with the felsic rocks, that's not for sure. You know, we don't have an idea. It might be before eclogite facies or during eclogite facies. After, I think it's difficult, because we should see tectonic contact in between the two, which is not what we see. Which is diffuse contact. So it's either the mafic rocks were tectonically created with the continental crust to form thick crust, and that occurred after eclogite facies. No, sorry. That might occur before eclogite facies. And eclogite facies was a result of deep subduction. So that's the contact here between the upper gneiss unit and the lower gneiss unit. And you see it's a nice malonite, solid state deformation, but in some places some leucosome is preserved, so some granitic texture, magmatic texture is preserved. So I think we can gain from that observation that this solid state deformation occurred short after or almost in the presence of melt. And the mineralitic and fibrite facies is transposing the synmigmatitic foliation. So now we're going to move below, not on this side, but on this side of the cross section. On this side here, we're going to move here. And that's structurally below. So here are the migmatites. For this kind of migmatites, where it's rich in biotite, lots of cordiorite as well, I think we can pretty confidently infer paragneissic potolith, so a sedimentary potolith. And you see here you have concordant leucosomes that corresponds to segregation at the grain scale of the melt, but they connect to discordant ones with a textural continuity. And these are mostly localized in sort of the hinges of small-scale folds. And these can be interpreted as melt migration out of the rock at further than the grain scale. So grain scale compaction, forming of the concordant leucosomes, and out of the rock, extraction of the melt, migration of the melt through the discordant leucosomes. And we can see the same things within potolith that we could interpret as orthogneices, because there are some K-feldspars, but it's not that obvious. Anyway, we see the concordant leucosomes and the discordant leucosomes in shear bands, and they connect to each other. So we can infer from these observations that in these migmatites were partially molten rocks, and they were affected by melt segregation and then migration, and that occurred during deformation. So that's another example of that. And then, if you go below, structurally, then we reach these rocks, which are more heterogeneous, dominated by quartz and feldspar, and with a kind of granitic look, but very heterogeneous, with lots of minerals that are preferentially oriented. And this I would call the diatic site. And it's difficult in these rocks to identify the potolith. You have here autoclays, so feldspar phenocryst, and from that you could say, oh, maybe it's a relic of the orthogneiss. But on the same place, you have cordiorite, which is an aluminum-rich mineral, and aluminum tends to be concentrated in sediments. So you think, okay, maybe you have evidence for sedimentary derived and evidences for granitic derived. And same here with this biotite sillimanite enclave which points towards sedimentary-derived protolith, and autoclaves, which points towards a magmatic-derived protolith. So the way out is to say, okay, maybe in these type of rocks, the gneissic structure has been lost, the solid framework has been lost, and it's a mixture. The dynamic was such that we have a mixture of different protolith mixed with some melt. You know. And that explains why we have evidences for both magmatic-derived and sedimentary-derived. Mixture of residual solids and melts, residual solids coming from paragnesis, from autognesis. So if we take that story into account, we have of these migmatites at a larger scale. Melting started somewhere around 350 million years, and that's seen in different places of the French Massif Central. And it's related to calc-alkaline and periluminous magmatism and placement of different plutons. These are the plain colors during the period of stretching parallel to the orogeny. And at that time, the formation was propagating towards the south. And later on, we have the large domes, this one, but also the Velay one, and a placement of granites that migrates. You know, if we look at here, it migrates from north to south. And it's also localized along this sillon houillé, this large transfer fault. And that's during a period of stretching perpendicular to the belt. So the first stage, tentatively, I thought maybe that's the orogenic plateau stage, where the belt, the crust is thickened, and its thickening propagates towards the edge, but also laterally, like for the Himalayas, for example. And the deformation front propagates perpendicular to the convergence direction, but also laterally. So that might be a record of that. And the last stage is a stage that is not recorded in the Himalayas yet, or not too much, but is recorded in the Aegean, is when you have lots of domes forming during a period of crustal extension, crustal thinning. And that's when extension is parallel to the convergence direction. That might be the period of gravitational collapse. Should I go further? You're in the Velay Dome. So this is the structural map that came out after that project I told you about, which was dedicated to the mapping of several 1 to 50,000 maps in the Velay Dome, with this uncertainty at first between the position between schist and granite, and with the migmatites in between. And all the structural work allowed to identify these structures, and you see the foliation is more or less following the shape of the first order dome, and within that we pick up some subdomes, like in Naxos. It looks fairly the same, although this is 100 kilometers. Naxos was 20 kilometers. So I worked on that, and I represented these large domes. So that's the upper nap, upper gneiss unit, the suture, and below that, migmatites with their dynamics to explain the mixture between paragneises and autogneises, and the subdomes with these concentric features that might resemble the subdomes of Naxos. If we look at the plutonic rocks that are emplaced on the vicinity or along this north-south section, that's north here and south to the left, we see that there is, here that's the distance from north to south, and that's time from 340, 345 to 290. And you see that there is a gradient, there is a trend of younging of plutonism from north to south. So the emplacement of magma, as was shown you on the map, propagates from north to south. Even what is called here the Vaugnerite. Vaugnerite is a town, Vaugneray is a town near Lyon in France, And it's where these very peculiar magmatic rocks that are rich in potassium and magnesium. These are elements that should not be in the same rock. We'll see that just afterwards for the last talk. Usually, magnesium is rich in the mantle, and somehow in mafic rocks, and potassium is rich in felsic rocks, in continental rocks, granites. So these magmas are magnesium, potassium rich. Should not be, according to Bowen's sequence. So the solution for that is to invoke, because they're so mafic in terms of the magnesium number, the magnesium content, that they can only come from melting of a mantle rock, of peridotite. A peridotite that had to be, so there are several ways to explain that. Either the potassium was incorporated at the place of emplacement of the mantle-derived magma, it incorporated potassium somehow, through freeze or mingling with the crust, or it's the source, the mantle source, that might have been contaminated by potassium. Does that make sense for you? Where would that continental crust come from in our tectonic scenarios? The one we invoked yesterday for the Phanerozoic. How we could transfer, in which tectonic context we could transfer elements from the continental crust into the mantle? Subduction of continent. If you have continental subduction, then the same process that happens for the oceanic crust might happen, like fluids might be expelled, and all the mobile elements, the big alkaline elements on the left of the chemical table, potassium, sodium, even calcium, might be released with the fluids and be incorporated in the mantle. And if this mantle melts, then all the potassium, all the mobile elements will go into the first melt. And this is a logic that is, so at first it seemed very peculiar, no? But I think I'll show you rocks just in a few slides. These rocks exist. Rocks with olivine and phlogopite, which is the potassium-bearing mica. And they are at the surface. So this, in purple, and even here, that records mantle melting. And this mantle melting occurred already at 330 million years and propagated with the felsic plutonism from north to south. So these are very important points to take into account in our, so that's the tectonic scenario, in our genodynamic scenario, how it relates to plate tectonics, lithospheric scale. So we have a diversity of magmatic rocks, mantle and crustal sources, younging from 340 to 310 towards the south of the Pluton emplacement. At the end, the last event is the Velay Dome formation, and that's the last event which corresponds to collapse and exhumation of the partially molten root. So in other words, during that time, from 340 to 3.5, some of the melt was extracted to form plutons, either from the crust or even from underneath, from the mantle. This probably remained partially molten, because it's difficult to imagine that at each time of emplacement of a pluton, you had to invoke an increase in temperature, and then cooling, another increase in temperature, and then cooling from 340 to 310. You see, it's continuous. It's not like pulses. So it changes totally the way of looking at the thermal evolution of the crust. Each plutonic event is not a thermal event. It reflects an extraction event, melt extraction event, which is different. So before we go to the geodynamic model, we just move area, and we go to this area in the Alps. That's Italy. That's the Alps. That's the Italian part, and that's the non-deformed part during the Alpine, or very slightly, and that's the internal zone of the Alps that we talked about the first day. And here what we see is really fantastic. Is the Variscan basement that was vertical and is now been tilted to the horizontal. And that's pretty much the moho for the Variscan basement. And what is green here is mafic rocks forming a mafic complex. The purple are peridotites, so these are mantle rocks. And then we move from granulite facies, amphibolite facies, migmatites, green schist facies with plutons intrusive in metasediments. And then these are volcanics of Permian age. And these rocks are dated, the mafic complex is also dated at Permian age. So it's, in other words, it's a section of crust that was vertical, and we see it now been tilted and has trapped the history at 300, 290 million years. Nothing much happened afterwards. Just a little bit of alpine deformation, but it's easy to take it out. So that's a unique example. You know, when if you're interested in how the crust formed from bottom to top, it's a pristine example. There are few of these preserved on Earth. And what do we see in the amphibolite facies, granulite facies? Metatexites of paragnaces, metatexites of amphibolite with garnet leucosomes and pyroxene. So all sorts of migmatites of different protoliths. They have recorded a pressure temperature gradient of about 40 degrees per kilobars. So that's mid-pressure, mid-temperature metamorphism. And what we did is sample rocks across two sections to look at the accessory mineral behavior. So zircon and monazite, how they would record that metamorphic gradient in one section. So here you can see the strategy. What do you think is the strategy here? So all the numbers here are samples. So we sampled across here and sampled across there. What was the strategy? I was asked several times about how should I strategically sample. So what is the orientation of the crustal scale structure here? Like this. The isogrades, these lines, like this. So if we want to go across the metamorphic gradient, you need to go perpendicular to it. So we're lucky there are nice valleys here that cross-cut all these structures, so we can easily sample. And why do two sections, one here and one there? What are the difference in colors on the map? What is predominant, the predominant color here? Green. So that's the mafic rocks. And what is the predominant color here? Yellow. That's the crustal rocks. So the idea here is to test whether the emplacement of this mafic body of magma at 300 million years affected the metamorphism, was the reason, the cause of high temperature metamorphism, or not. So if this is correct, if the emplacement of the mafic magma is responsible for high temperature metamorphism, we should see different behavior and different gradient of metamorphism in this section and along this section. If not, then it should be the same. And actually, I think we have already part of the answer. You see the dotted lines here, this one and this one, these are the isogrades. What do you see with the isogrades relative to the shape of the contact with the mafic complex, which is here? Which one is cross-cutting which one? Thank you. Simple. Geometric relationships are very important. And people still today claim that the emplacement of the mafic complex is the cause of high temperature metamorphism. You have a simple answer there. Mapping, if it was done correctly, shows that emplacement didn't affect the isogrades. Cross-cut it, but doesn't affect it. If it was that was responsible for the high temperature metamorphism, we should see the isogrades going like this. It's a very simple geometric relationship. The answer is in the field. We did fancy things with the accessory minerals and so on, but the answer is in the field. So what do the zircon look like? So first we start from far, from the low grade, and in low grade we have ages. No, all these ellipses are ages on the zircons. 580 million years. So that's the Pan-African. No hint of Variscan metamorphism. And then when we start to pick up the amphibolite-facious rocks, then you still have the cores that are inherited from the protolith, but they have rims that are younger. And there's two different type of rims, one which is inner rim and outer rim, and these ages are different. So you have here Variscan ages, almost 300 million years, and also Permian ages. And as we go down the structural section, then you see the zircon core is smaller and smaller. What does it mean? What happened to the zircon? It was dissolved. And if it's not dissolved, there's no zirconium in the rock to form zircon. So that's a condition to form new zircon is to dissolve the previous one. Because zirconium is pretty much only in zircon. There's no zirconium not very poor, very little in garnet, very little in pyroxene. It's possible to have some reactions providing zirconium, but most of it is in zircon. So if the zircon is not dissolved, there's no new zircon. And dissolution of zircon happens at 800, 900 degrees, high temperature. And that's why we have preserved in the low-grade rocks mostly the zircon cores inherited from the previous orogenic history. And as the temperature increases, then the zircon core is smaller and smaller. And I think actually this is not an inherited core. The limit between inherited cores and new zircon is here. And these are from the granulite. Granulite's almost only new zircon, with ages spanning from 360 to 270, so the Variscan history. And if we look at how these distribute with respect to the Concordia, so for the bachelors, you haven't been, I just showed it how it works yesterday, but it might be a bit too complicated. So you have two different ages, the 206 lead, 238 uranium, 207 lead, 235 uranium, and you see that the data, each ellipse is the data, are pretty concordant. Same here for this sample. And they spread from 320 here to 260, 320 to 270. So what do we do with that data set? That's where we're in trouble with the geochronologist. So I'll explain the position of the geochronologist. I gave you a hint of that yesterday. So the geochronologic person has just acquired €1 million or $1 million machine to acquire the most precise date as possible. And his date is this, right? That's his analysis. The problem is how this date translates into an age. And there's some confusion in the head of the geochronologist that he wants this age to be as precise as possible. The goal for him, from my perspective, is to get this as precise as possible. The age, that's my problem, the geological problem. Do you see where I'm going? I think the resolution of the machine, which I agree he wants to show that it's very precise and so on, that should be on this. How small the laser spot could be, and how much material he can detect with the mass spectrometer, that's his job. Interpreting that into an age, that's our job. And there's some confusion, because they want to have that age as precise as possible, which is inconsistent with physical processes. This has a duration. It's not a snapshot. The geochronologist wants it to be a snapshot, but nature is telling us this has a duration, and it might be a long duration. So with the statistics, you might find groups of dates that define discrete ages that are significantly or not, that's we discussed with geology, significantly different with the main standard weighted deviation that is around 1. Yes, you can do it. But what justifies that? It's just statistics. That's for you. Just playing with the statistics, you'll find the way to restrain your ages. In your case, it might work, but not in metamorphic rocks. The other way around is to consider that this is the duration of the high temperature event. All this, the 30, 40 million years. And the same for granulite facies, right? It also spreads over tens of million years. So I think the demonstration comes from comparison of the different samples from the different structural levels. So I just flipped the section to make it in a way that where the low crust is here and the upper crust is there. It's easier than having to go like this, although you're good at that. Huh? So these are the results going down structural section. And you see here that the black are R1, the first rim. The orange is R2, and systematically R2 is younger than R1. And the blue is what we call the stubby zircons that are kind of trapped with an aspect ratio of around 1 to 2, not too much, not very elongated, and are uniquely Variscan. And the blue ones are systematically younger than the black ones. And if you look at the histogram, this is the number of data as a function of age. You see the distribution of dates, which you can find peaks in there if you want. But you can also consider that this is an age spread that records the high temperature event. What do you think characterizes these different histograms from top to bottom of the structure? The same scale, huh? That's the same time scale has been used for each of them. What do you see? Well, if we would think about thermal peaks, at least the peaks should be consistent from one histogram to the other, because there's no reason the crust would record a thermal peak in the lower crust, but not in the upper crust, or the other way around, in the upper crust, but not in the lower crust. So do we see coincidence of peaks? It's difficult. We might be doing that. But I think what is more compelling from the distance is the shift. Systematic shift from, so it's old to young, from top to bottom. What could that represent? We have a record here of high temperature crystallization of zircon. High temperature crystallization of zircon shifted in time from top to bottom. Do you think what could explain that?
So the high temperature event started at 340 million and it goes on till the yellow ones form.
Yeah, so that's a good idea, but we're just going to reformulate a little bit. Was it the onset of the high temperature or the end of the high temperature?
Onset of the high temperature is 340, so the
Yeah.
starting of the graph, and then the ending of the high temperature is the yellow.
Because we tend to think mostly in terms of prograde. But what is mostly recorded in metamorphic rocks and in zircons is retrograde. So we might have preserved the onset here, but here, as we go down structural section, it's probably the cooling that is recorded. Does it make sense to have cooling from top to bottom? So the isograds would go down the crust. So that shift, I think, might represent cooling, progressive. So the isograd that was responsible for zircon crystallization, let's say 100 degrees, was going down from 340, 320, 310, 300 million years, 290. So we have here a record of crustal scale cooling at the end of orogenic evolution. Did that remind you something about what we talked about yesterday, the thermal models? No? After the crust has been thickened, the temperature rises, and when the crust thins, the temperature goes down because there's less radiogenic heat production. And that, I think, is recorded here. Cooling of the crust. It's now 25 kilometers thick, but we have all the record that is similar to what is recorded in the Variscan belt elsewhere with the high pressure rocks. I didn't talk about it, but they are there. The high pressure rocks are here in the middle structural position. and then all the high temperature rocks. It's all the story that we could tell from the Variscan belt elsewhere is recorded here in the Alps, in the Via zone. But then we have mostly the cooling. So I finished with that reconstruction with a first period which was similar to what other people proposed of oceanic subduction, followed by continental subduction. But then comes into play the melting process. Rocks probably started to melt in granulate fissures and maybe even deeper, but partially molten rocks only record the retrograde path. So we might not have a record, or we haven't found a good tool to identify this. Maybe zircons might be starting to pick up the high pressure. And that might be a tool to get that in the future. And then here you see the mixing between the continental crust and the oceanic crust with some pieces of mantle. And then these pieces of mafic rocks and ultramafic rocks are mixed with the continental partially molten crust, which is exhumed back to the surface, and that's the high pressure going into lower pressure, decompression. And then, so the high-grade nap is on top, and below that you have the mid-pressure migmatites, which represent the partially molten crust beneath the high-pressure rocks. And that looks fairly similar to what proposed for Tibet yesterday. And then at the end, as this slab retreats, and that explains the north to south migration of magmatism, metamorphism, deformation. I should say the other way around. Deformation is actually also followed by sedimentation in the foreland. The same record, I didn't talk much about it. So deformation front migrates towards the south, and then plutonic front, and then metamorphic front. Everything followed the same trend. And that's consistent with the southward retreat of that slab. And then at some point, it reaches the Gondwana strong limit, stops, and that's the time of collapse. So we go from thick crust to thin crust. And that's the time of exhumation of the partially molten rocks and then cooling. Okay, I think I'll finish with that. And you see that also here, you have a lot of magma transfer in that model. And that magma transfer will lead to crustal differentiation. And I'm going to insist on it just a bit more in the last lecture later on. Yeah, that's what I wanted to say here. So this magma transfer will lead into layering of the crust and redistribution of material that leads to crustal differentiation. Okay, that's for the Variscan. It's good timing? Questions? That's the typical cow. I know that you guys are fond of cows. So that's the typical cow of French Massif Central. We call it the Salers. Nice looking. No, you don't have that. You don't have these ones, huh?
Oh, we have gearwax.
Yeah.
So regarding the concordant, the discordant equilibriums which you suggested,
Yes.
how to differentiate that from the granitic veins?
Yeah. Yes, that's a good question. So I think there are several evidences criteria that you can use. But it's a very good point. First, the regional relationship, the metamorphic gradient. Where you are, where is the rock relative to the isograds? Is it in the sillimanite isograd or in the sorrelite isograd? In other words, are these leucosomes consistent with the mineral pyrogenesis of the host rock or not? No? Are they consistent with them being a melt extracted just from the rock around it? And then also the textural continuity between concordant and discordant. So that, I think, is a good evidence that this was melt at the same time and then crystallized from the melt. If you had a granitic vein, it should cross-cut. And usually granitic veins that are in the thermal disequilibrium with their host rocks, first, they don't have the right composition to come from melting from the host rock. And then, if they are in thermal disequilibrium, you should have sharp contacts, or brittle contacts, and also maybe a reaction rim on the edges with crystals that are crystallized perpendicular to the vein contact. You have all sorts of criteria that you can use. Chemical consistency, mineral consistency, diffuse versus sharp contact, and the texture of the vein if you have minerals that are growing on the edges that reflect thermal disequilibrium between the melt and the ethos. Okay?